So, first of all, welcome everybody. And I'm going to take the speakers in last name alphabetical order. So the first one will be Ben. We have about 2 minutes each. So let's see if we can try to stay close to that. Ben, can we hear you? Evidently not.
I hope you can.
I see you.
Steve.
Yes, yes. I
Thank you
can
very
see you
much.
and hear you.
Excellent. For everybody, I hope. My name is Ben Bennett. I am the Director of HPC Strategic Programs. Catalyst UK is one of those programs. It was born out of a conversation we had as HPE with the UK government towards the end of 2017. And then ourselves and ARM had a joint announcement in April of 2018, and we kicked off at the end of 2018. This is a program for ARM software to expand the ecosystem. There are 3 sites in the UK, each with identical machines. These machines are homogeneous. So they're all ARM. ARM supports the development. They're based around ThunderX2. We've been running for a couple of years now. And if you go to my talk, not now, of course, but if you go to my talk, you will see more details about the systems, the work that's been done on them from a system software standpoint, and the science and research that has been afforded the scientists.
Steve, are you on mute?
Next, we'll hear from Tim Costa. Maybe not. Okay. Let's see if Tim's on. Nope, don't see him. So next, how about we go with Cosimo? He's not on either. Excellent. We're flying through these people. Oh, well, okay. Next is Gorda.
Thanks, Steve, for the wonderful introduction. I'm Brent Gorda, and I am the Senior Director for High Performance Computing here at ARM. You see me still on the show floor at SC'19. I'm such a fan. I oversee the HPC activities here at ARM on the business side, and I'm excited to be participating in the next generation of architectures for high performance computing. I've been around HPC for as long as everyone, including Ben and Steve, and am very happy to be among friends as we go to try and make an impact on future HPC architectures. Thanks.
Awesome, thanks, Brent. Next, Lynn.
Hi, so I'm Tim. I work for SC'20, and we are primarily sort of coming about this from the point of a user, although we sort of sell our services as well. Generally for the surveying industry, for geological surveying. And we do a lot of processing using finite difference HPC code. So we're generally using Intel, but I think our experience is porting our code to ARM64 had been it went so well that I think it was worth writing it up and giving a talk. So mainly I can sort of share my experiences from a user and porting code perspective.
Okay. So next we'll hear from Jean-Marc.
Hello, can you hear me?
Yes, we can.
Ah, perfect. So Jean-Marc Denis, I'm the chairman of the board for the European Processor Initiative. And I'm also the chief of staff for the Innovation and Technology Division at Ethos. And I've been in HPC forever. That's it.
Okay, next we'll hear from Craig.
You're on mute, Craig.
Yes,
There you go.
once I moved to France, I mastered the art of mime. So my name's Craig Prunty. I'm VP of Marketing and Biz Dev for Cypro, based in just outside of Paris, France, in Maison Lafitte. For those of you who don't know, Cypro is a fabless semiconductor company focused on HPC, well, HPC in other markets, but primarily HPC for exascale for European markets.
Okay, next, Stefan. Stefan. He is not on. Okay, so after, how about Toshiyuki?
Hello, my name is Toshiyuki Shimizu from Fujitsu. So I'm leading the system development of the supercomputer Fugaku. So that's it. Thank you.
Thank you. So last but not least, Jeff.
Hi, I'm Jeff Whittick. I am head of products at Ampere, and we've developed a new CPU from the ground up, really focused on the needs of the cloud. But included in that cloud usage are computationally intense and HPC workloads. And so our Ampere Ultra processor is delivering extreme throughput computing. We're seeing some really great results in this space and excited to share them.
Awesome. Stefan is trying to find the unmute and video buttons. Is he?
Got it.
Excellent.
I am promoted to a panelist now. So now it's there. Now I can see all of you. So hi, my name is Steven Sachs. I'm a senior application engineer on the HPC application performance team from AWS. And we're super excited to be able to provide the Graviton and Graviton 2 instances. They're based on ARM processors. And in my talk, I'm going to give you a quick intro into how you can actually go ahead and run your HPC jobs on those really quickly. So we're really excited to see your results.
Excellent.
Steve, I wonder if Fabrizio is here in place of Cosimo.
I was just saying, I am here in place of Cosimo Gianfreda, who had a sort of conflicting agenda in these days. So welcome everybody. This is Fabrizio Magogliani with E4 Computer Engineering. We are a system integrator, and our love story with ARM started when I was younger and I had all my hair. So you imagine how far away it is.
I like the love story. That's great.
Oh, well, you will see Cosimo is even better. So I think that I know all of you beyond 40 years old, and we want to stay into the ARM space. That's why we are members of the European Processor Initiative, of which I see two representatives here. And it will be my pleasure to join this team and to learn from them how to improve our products.
Excellent. Thank you all. I guess now we want to move into questions and/or I don't see any questions there. So I've got the first slide up. That was some of the questions were posed. I have a Q&A. there's an anonymous attendee, which is interesting.
Can we read, Steve, can we read the questions or only you can do that?
Can you see the screen that I'm sharing?
Yes.
Okay, so do you want me to read the questions on the screen that I'm sharing?
Yes, please.
Okay, so the first question that was posed, and this was just a seed question. Anybody that has any others can certainly feel free to pose them. And I believe you posed them over in the other one. But the question was, what was the driving force behind you choosing ARM as a processor partner / technology?
Well, I'm happy to start with that one.
Okay.
So there's two real reasons, of course. Is that number one, it's the customers were asking for it. And if you don't build what the customers want, they tend not to buy it from you. And then the other thing is our CTO office has been working for a long time looking at technologies and looking into the future for applicable technologies. So as you know, we were working with Cavium, Marvell as now, other vendors, and we're working with Fujitsu on product. So it really comes down to what your customers want. If you, as I say, if you don't build what your customers want, they'll go to somebody who will. So we built what our customers want. We have deployed it. There's currently the Marvell platform and also the Fujitsu platform. I can't give you a detailed roadmap 3 to 5 years out, because as we all know, all roadmaps move to the right. But what I can say is that we are processor agnostic, and it comes down to customer demand.
I take the question, and I agree with Ben. We have to, E4 is going to follow what the customers are asking. So I add something that we should provide our customers multiple choices of the architecture that they can choose in. So that's why E4 is providing x86, ARM, as well as open power. And our job is not just integrating systems, best systems, but also providing these and recommendation to our customers. That's why we are agnostic, as well as Ben mentioned, and we want to provide the best solution, no matter what is the architecture of the processor. And that's the key for success.
And I agree with Ben and Fabrizio as well in terms of the customers asking for it. For us, I think it was about three things. It was about flexibility, it was about efficiency, and it was about performance. So ARM gave us the flexibility to build what we wanted to in a way that other architectures wouldn't have given us that ability, and to ditch a lot of the old legacy features and kind of unused architectural pieces. And that gave us a lot of efficiency, both in terms of power efficiency and also in terms of area efficiency, which was very important for us because of how we're scaling out core count, and then performance, which clearly over the last couple of years, ARM has demonstrated through the architecture and through the IP that, right on par and leading when put up against x86. So kind of a perfect choice from our perspective at Ampere.
So Steve, I'd like to add something as well. So from the SciPro perspective, we're partnering with ARM on a number of things, but obviously IP is important, but the real elephant in the room here is ecosystem. And if you're going to look at an ARM server, or if you're going to look at a server processor, you need the ecosystem to be in place. This is something I think most people in this room have worked on over the last 12 years, let's say. And I would say, 2.5 years ago, it started to become self-sufficient. So you had people, you have more and more hackathons, user groups, developing applications, porting applications, optimizing applications. And this is a must-have. in Europe, you hear a lot of buzz around RISC-V, and RISC-V has its value, but it's an embedded processor right now. It is not a server processor. ARM gives you the capability to build a server processor.
Yeah, let me add a few words. I've been on mute. This is why I couldn't enter the discussion before. So I do agree with everything that's been said. What is very, very important when you choose an IP or an ISA, this is the quality of the IP. This is how open is the ecosystem, how rich is the ecosystem, what's the right fit between the architecture or the IP with the targeted market. And with ARM, in the HPC space, we have everything together. We have a very, very well established IP ecosystem with proven performances. We have the flexibility to build the architecture that we want for the European ecosystem. We can have access from IoT to data center to the complete market space, and this is crucial for the evolution of the European ecosystem. And we have learned a lot from all the projects we have run in Europe, starting with Mont Blanc in 2010 up to now. So we know how it works with ARM. We know how we can build from ARM. We have the people, we have the expertise, and we start having the user ecosystem. So for us, at least for the next 2 generations, ARM is just a must.
So I would like to come in there regarding the ecosystem. One of the reasons that the Catalyst program existed was to expand the ecosystem. A lot of the ARM systems being shipped were using ARM as a computational hammer. It had more memory channels, and so therefore competed very well and very efficiently with some of the code. Where we are seeing some issues is around the non-computationally intensive work. For example, using ARM as a Lustre server. And that's not a function of ARM, it's purely a function of the maturity of the software. If you look at the very, very early Beowulf clusters, those things were unstable as heck. It's nice to know that the ARM systems are not unstable, but we still have a long way to go if we're going to be able to put our hands on our hearts and say that you can, in a large production environment, just drop an ARM server in. There's nothing to do with ARM, it's purely that there are still more bugs to be found.
So
there is
sorry.
Go ahead. No, go ahead.
Okay. So now I would like to add something about the ARM. So ARM ISA is an open architecture. So we can use the ARM architecture and widely used. There is a good ecosystem of the ARM, and it has also capability to grow while it is maintained well for compatibility and portability. So Fujitsu had an opportunity to collaborate with ARM to extend its ISA for HPC applications. It is a reason why we choose the ARM architecture. So we believe that we can extend the performance and so applications for futures.
Okay, on this page, there's sort of in the middle, it says, given the big advantage of fast memory and the HBM2 based A64FX, are we expecting to see ARM designs that use HBM and DDR to balance performance versus capacity?
If I may, I would like to start. Jean-Marc speaking.
Sure.
Let's define at first what performance means. When we look at the evolution of the HPC space, we see that performance is not about just double precision floating point operations. It's becoming extremely diverse. I mean, you have FP64, FP32, BF16, integer operations, so there are different meaning for performance. This is why we see so many accelerators coming up on the market. And this is why the role of the CPU is going to change big time. Up to now, we expected to have the CPU to deliver the performance engine of your supercomputer. Now it's changing. We've seen with GPU that it already has started to change. And in the future, we'll have GPU, neuromorphic, quantum accelerators, whatever diversity in the accelerator space. So the role of the CPU is going to change a lot. And this is why the CPU has to be defined totally differently. From this aspect, the main role of the CPU will need to feed the accelerators and to be the most balanced and breathing system for the data can move in and move out very quickly with extra low latency and extra large bandwidth. This is why, and I'm making the bridge with the question, we need to have both HBM and DDR in order the accelerators are well fed and in order the data streams can move in and move out very quickly. And one of the beauty is that you can make your choice in terms of number of HBM stacks and number of DDR lanes as well. So depending on your characteristics, on the application profile, on the vertical you target, you can balance that the way you want. I'm finished.
Okay. There was a question posed in the chat session was, can the panelists comment on AVX versus SVE? And not everybody has to answer at once.
I think we had that answered by John Stone in the applications area, who expressed a preference. I don't know that the.
So,
go ahead, Steve.
So do you want that that question sent to that panel?
That might be a good idea to send it over to them as well. But in short, he was indicating that the SV implementation was much simpler to deal with because of the pre-loop, post-loop activities that you don't have to do. It's a very interesting talk. Maybe somebody can post the link to it here if folks haven't seen it.
Okay. So just a real quick comment. So from the Los Alamos workload perspective, we have been interested in ARM for quite some time quietly for various reasons. And one of the reasons that we were interested in ARM is the fact that many of our code seems how we sort of live and die by computational fluid dynamics to some first order, whether it's whether it's finite element, finite volume, or finite difference. We don't do too many spectral methods. Our interest was in SVE and HBM. So those were the two driving forces for us to not only fund some companies to work in the space, but for us to choose ARM, because as everyone else has said, it's an open ISA, and I can add to it when required. So that was one of the reasons that Lannel chose to go down the ARM path. And one big difference that Lannel has is 128 and 256 bit or 128 bit vector lengths don't help us too much. We like 256 or 512, and we like either 3 or 4 of them. So that's my hope for silicon. So next. So I'll read the question. In what area can the community enable a richer ecosystem and a broader non-cloud HPC market. I'm not sure what the on-prem is, but I'm good.
So I'll have a poke at this one to start with. I think one of the things that we all need to do is we all need to be cheerleaders for high performance computing. We need management, we need finance people, we need business partners to understand what HPC can do and why it is of value. And if people understand it, I'm not suggesting they understand the nuts and bolts, but if they understand the value it brings, then it's a much easier conversation to have, and it's an easier conversation to have about deploying it. The more we deploy it in the more areas, then the more different types of problems we have to solve, and the bigger range of different types of problems we have to solve is going to expand the ecosystem, in my humble opinion.
This is Fabrizio. I agree with what Ben said. I think community is key to point where the vendors should invest their resources and sort of driving our technological choice. The alternative is not between HBM2 or SVEs and whatever. Is doing a system which is serving multiple users and multiple applications. In Europe, we are using the approach of modular computing, where one size does not fit all. There are different systems, different partitions, which are serving different applications. And the community, the users, are providing their applications, and this is a very useful cycle, because at that point, when we know exactly what the users are looking for, we can provide the best hardware solution and the ecosystem.
Okay. There's a question, says, do you see some form of standardization of matrix multiplication API acceleration macros, which would stop that scrolling, efficiently mapping to matrix multiply instructions for CPUs that would allow easier use by developers of SVE2 matrix mul, Intel AMX Power matrix mul? I don't know. So this is a request for a common API for doing like FMMAs.
But I think there is already the DGEM or SGEM who is taking care of matrix multiply, that relying on the libraries, the BLAS level 1, 2, 3 libraries is the best way to get the best performance out of the single architecture.
Yeah, that seems reasonable. Otherwise, we'll have to reinvent the wheel, which is always extremely exciting. Go ahead.
No, well, I think that we should work at this point at a higher level than just the basic BLAS level. We should work on the structuring the code to exploit the best feature of the code for the system.
Yeah, so I guess one of the questions that would probably go to somebody like Linford would be, what does the compiler need in order to generate like things like FMMAs, which they're in the 8.3, 8.6 version of the spec, because by default generating an FMMA is not something that most compilers are currently doing.
That's a good point. I think you know, if we're going to call for a standard API for matrices, we should look for a standard API for vectors first. That's something that's been challenging for the community for a long time. There's a good video on InSimD in the AHUG YouTube channel that you might check out. So that would be a starting point for this kind of thing. Then going lower into the compiler, I know there's active research into using things like MLIR. Google has been active in this space, trying to find ways to make the compiler smarter about identifying opportunities for generating matrix instructions. Personally, I feel like that's a bit of a long shot. That, you know, it's nice to have smart compilers, but to really optimize for the architecture, it's going to take a ninja at some level. And once you have a ninja, you might just go ahead and deal with the instructions directly. Which fortunately I've found to be fairly easy using the ARM ISA. You know, it's not as complicated as some other architectures I've worked with. It's you know, there's no silver bullet, but definitely starting with a simpler problem, starting with how do we improve vectorization in one dimension would be a good place to begin. And then we look at vectorization in 2 dimensions.
So I guess before we got to, I've been doing this for way too long. I've never met a brilliant compiler yet, sorry. I used to be on Ken Kennedy's review board, and he was about the closest I could come to one of those. So intrinsics or useful library calls from the vendor is always extremely helpful. There's another comment. Focus on areas where specialization and cooperation can be enabled between vendors, such as SIXL. I think that was a question. And I'm assuming that one of the silicon vendors would want to comment on that.
Yeah, I'll take a jump at it, Steve. So we see common interfaces like CXL as important, and it's important from a processor vendor point of view because it allows us to build one interface instead of 10. That said, it doesn't do everything. So today, our first generation will use C6 as an interface because the features we want in CXL weren't available yet. We are members of of CXL. We will implement CXL, but that doesn't mean that we won't keep other interfaces or capabilities to mux with that interface when the features are differentiated. In terms of community standard, there's another thing that we're looking at here in Europe is a common platform through the EPI, the European Processor Initiative. And this is a way to build a platform that can be used, can use multiple technologies, potentially in the same package, potentially bringing in IP or outside of package across links like CXL. So it absolutely makes sense to share IP where you can and get a multiplier from IP from multiple companies. And things like CXL standardizing interface like that, it makes it a lot easier from the processor company point of view, because for these large chips, I think most of the people here building HPC chips would agree, you're pretty much IO limited in a lot of your designs.
Okay, so there's a question that is it's a statement, but I think it's an implied request. Porting standard community applications, I would also put in potentially benchmarks, to ARM and making sure they perform as good as possible out of the box. I don't know.
So Steve, one of the issues here is that ARM isn't ARM. And a lot of the wrapping around the actual compute core, for example, the amount of I/O, the amount of memory access varies. And so one of the issues that we're going to see is people are going to make assumptions that because you've ported a highly compute intensive application or library to run on, say, ThunderX2, and then you take it to the Fujitsu processor and the Ampere processor, we have to have another hack at the processor again. And so, yes, it's really good that we have this organization, but we have to realize that, you know, ARM processors aren't all the same. I give you, for example, this thing. So we have many more people working on it, but we have to be careful when we're making the assumption that because it's ARM, that everything is going to be fine. And that's some of the issues we're finding on Catalyst at the moment.
Let me add a few words. When you need performance, you are going to move on accelerators. I'm sorry to repeat once again, but this is what we observe today with CUDA and tomorrow with maybe something different or aside of CUDA. So what will remain in the CPU is what cannot take advantage of the accelerators. So that will be very complex operations on subroutines on kernels, extremely complex in the sense that the behavior or the kind of kernel is very difficult to adapt to one given accelerator. This is why what is very important is to have good enough performances out of the box, as it is mentioned on the remark or on the question. So from this aspect, the complexity pressure, which is the opposite of the inverse, sorry, of the byte per flop ratio, is crucial. It means that you don't change your application, you compile, let's say -0.3, and boom, you've got very good performances close to, let's say, the peak of your CPU with no special effort. This is why the key parameter to consider here is the byte per flop ratio, not reducing the flops or the performance level, just to have something that is in the HPC space, but improving the memory bandwidth. So once again, it drives to the question of maximizing HBM and DDR simultaneously on the system. And this is the only way, in my view, to get performances out of the box for any class of applications or section in your application that cannot take advantage of accelerators.
And I also add that the megaflops, teraflops performance is not the only objective of a system. There is also a key component, which is energy to solution, which is going towards exascale class architectures. This is going to be the most, well, in my point of view, one key parameter to take into account when we measure how a system is good for doing something.
So I'll just make one comment, and I don't want to get into any pseudo-religious wars. Many of the codes that we have, at least at Los Alamos and some other places, are not necessarily amenable to GPUs. We have been working on trying desperately to get them to be amenable to GPUs for the last 8 years. But some of our codes, no matter what we do, we can't get them to run even as fast on GPUs as we have on CPUs, which is one of the reasons why I mentioned earlier, and I think this goes along well with some of the other comments. That's one of the reasons we desperately wanted SVE and HBM, and that's one of the reasons we funded a bunch of work in that space. But we do also agree that there are some of our applications that run very well on GPUs. It's just unfortunate that it's about 10 or 15% of our code.
So Steve, I'll cast my mind back to about 15 years ago, and I gave a talk at the PPAM conference, and I said that one of the natural consequences of so many transistors was the rise of heterogeneity, the ability for different bits of silicon to specialize. However, I would like to point out that Fugaku is not accelerated, and some of the results coming out of that are really quite interesting in terms of efficiency and performance. So I wouldn't write off CPUs, and as Steve says, that we still have a long way to go before the software enables us just to plug in the right accelerator for the right job and for it just to run. I'm not saying that we're not going to have specialist silicon, but I actually think we're further away than a lot of people think we are.
Right. I wasn't throwing away CPUs. I was just saying that GPUs don't answer everything for us. And we do have some of the small Fugaku nodes that we're testing some of our open science codes on.
Yeah, to some extent, at the upper level, at the supercomputer architecture level, the conclusion from what we said is we need diversity. So we need some sort of modularity, with one module being full CPU, one module being with GPU, another one with FPGA. On the size of the module at exascale level, the size would be a pre-exascale, or let's say a few hundreds of tera operations or tera performance for each module, and whatever the definition you give to performance in this context.
Right.
And that would be the proper architecture at the exascale level. I'm not talking about exaflop. I'm talking about exascale. I mean massive systems, let's say in the range of tens of megawatts.
Don't disagree. That's, I mean, yeah, I agree. No more comment required.
Steve, if I could interject just a second here. A year ago is when we started getting serious about forming AHUG, and you see that this is the first event of the community. We are starting an activity that will focus on applications, both porting and performance to the various ARM ecosystem silicon partners. And I know it's been going on in various pockets here and there, so we're gathering up what we can about that. And you can expect us in the new year to start talking about how we can coordinate activities and make sure that we're optimizing resource usage to get to the point of portability of applications, and then the next point of specific optimizations per platform on these applications. I think it's evidence of a emerging and maturing community for ARM and HPC. So I take it as good news and present it that way.
Excellent, thanks, Brent. So the next question, it just has a circle with answers. Can the traditional HPC market support more than one vendor? I think the answer was yes. That was a fluff question. Okay, what lessons can ARM and ARM-related vendors learn from recent RISC-V developments to improve their position and support for traditional HPC? Do you want me to read the comments, or does anyone on the panel have a comment to make?
No, if nobody's going to jump in, I'll jump in. So again, RISC-V has a lot of buzz in Europe. I don't know what we're going to learn from RISC-V other than what I said before, which is ecosystem matters for server processors. You can't just show up with a processor and expect it to run in servers. Most of us here remember when we finally got, Ubuntu, SUSE, and Red Hat running as OSs on ARM architectures. That was a big deal. It took a long time. And then it went to the next step was getting the virtualization and container support in the middleware. And that took a long time. And then applications, I mean, it's a lot of work, and it's a lot of companies and a lot of people. So RISC-V could be very interesting as an embedded processor, and that can have applications for acceleration, certainly. But thinking that RISC-V is going to be a server processor core CPU in the next, I don't know, several years, let's say, conservatively, is not realistic. So I don't know if that's a lesson learned or not. It's nice to see new architectures come out, and it's nice to see a lot of buzz around them. But
I would turn it around, Craig. I would say I think there's a lot that the RISC-V people can learn from the developments in ARM. Ecosystem is everything. We know that there is still lack of stability in drivers. As you move on towards the edge of more esoteric and larger systems. There are no, as far as I'm aware, large RISC-V HPC-based systems that are performing at any level like any of the ARM systems. So I would turn it around. Yes, RISC-V on a piece of paper looks fabulous. Stick it in a data center and try and mount Lustre on it, and I'm guessing the answer would be slightly different.
And good luck, right? Yeah.
Yeah, I'm not going to say that.
Yeah.
Putting Lustre on anything is a religious experience.
Yes, akin to slitting the chicken's throat and splashing blood everywhere.
Exactly. So there are two comments that I have agreed with. One is the lesson is architectural flexibility to respond to application needs, domain-specific silicon, a la Patterson. That is, and that's sort of in my mind tied to the middle top answer, which is ARM, the company, should be easier to work with.
I completely agree with that. They're terrible to work with.
Keep going.
The one thing, and this goes with what everybody has said, I see RISC-V as an experiment and an experimental architecture that if you want to just to try something like to do 64 or 128-bit pieces of a core, you can do it without having to float alone from Lloyd's of London. So that I think is and I think ARM has seen that. They will have to speak to that themselves, but I think they at least see that that is a valuable tool for those of us who design new processor complexes.
So there's something called flexible access where ARM has responded with respect to the upfront costs of things. I invite people.
Right. I think that process, the more it becomes available, I think it will boost ARM's visibility, capability, and saleability, because there will be a lot of people trying to tinker to develop new things. If you look at the major step that Fujitsu deserves a lot of credit for, of actually going and developing a system around the ARM processor, that was awesome.
Yeah, maybe I can jump in here again, Steve, at the risk of speaking too much. So we're partnering with ARM. We're a startup. We're experiencing exactly what Brent said, which is they're helping us along with IP. They're working with us on our design for the optimization. And as a startup, we're backloading a bit our payment structure to them because we're going through Series A funding now. So that's something you don't get with sort of an off-the-shelf open source processor design, or you couldn't get. So, there's a lot of value that you get out of ARM in terms of, again, IP, and part of that is their POP IP, their development IP.
And I have to say that as an OEM, their support for Catalyst has been outstanding.
Just got another circle. Awesome.
And I didn't even touch it.
So I do want to say something about a RISC-V. Again, this isn't anything against RISC-V. It's just not ready to be a central CPU for a server. So there are applications that it can absolutely fit, and people can build big processors with it, along with other architectures, right? It's really, again, it's just down to what works in servers. And if you're going to build a server, you need it to be used. You need an ROI.
Right, I agree. I think of it more as a hardware Raspberry Pi almost. Something I can tinker with, and if it works, it works. If it doesn't, life moves on. I can experiment with a functional unit that I might want to try and see how well it works. Awesome, I think. Here you go. I think we're back to the beginning. Nope.
So if I can, I'd like to draw attention to that, that last slide you showed had 5 votes for the South Korean architecture. The K supercomputer, which I think is not necessarily a good name, having been used once. But I invite people to go take a look at what the Korean supercomputer CPU presentation is, because it mirrors a lot of what we've talked about here. It's a Zeus design with an accelerator on chip. And they're very open with respect to what that looks like and how they expect it to perform. I think it might be an interesting one for folks to go check out. Given that it got some votes too, some people have already.
Yeah. So here's some questions in our last 2 minutes. And I think the top left one is sort of at least been briefly touched on more than one occasion. Brent, did you have that paper, or could you send that paper out on Xeon versus SVE? Or
I think John typed it into the chat window. So if you're following along, just click on the chat window, you'll see it.
Okay. Well, when will, yeah, this is a question that's more of a product and a forward-looking question to ARM, which may be a difficult one to answer. And that way Brent can answer it and get in trouble. When will we start seeing ARM IP mixed with on-chip accelerators like we see in mobile? Is ARM doing anything to make such systems easier to build, program for servers like Intel?
So again, I draw your attention to that South Korean talk, because that's what that is about. The hardware architecture silicon is emerging.
Can RISC-V replace ARM? I think we've sort of flogged that one for a while. At least, not within the next 6 months, maybe even longer, like 6 years. And this one, I don't think that this one really can be discussed because it's a problem from a legality point of view. What is your view on the ARM NVIDIA acquisition, and what effect do you think it will have on ARM expansion in the cloud and HPC? I think from a legality point of view, it will be very difficult from someone from either ARM or NVIDIA to address that, because if they're in a process where they're having discussions about that, there are more legal rules in the United States about talking about things like that than you can stuff in an encyclopedia on a multi-petabyte disk drive. But if Brent wants to make a statement, I think we're all listening.
I'll pass. Thanks, Steve.
Yeah, it's always that keeping your job process. There's a kind of a boulevard for ARM processors to enter massively on the market. We've seen this before, announcements from ARM-based systems than before. More of this. How can you ensure ARM vendors will be ready in time with ARM processors with nice features like HBM? Brent?
Well, I think that's up to each vendor, right? We're already seeing that Fujitsu is well ahead of the competition with respect to that individual feature. We're already seeing other vendors come to market, such as AWS, with ARM-based server processors. And we're seeing many others, some announced, some not announced, with roadmaps of when they expect to be present. And again, a lot of this is enabled by this community and the whole ecosystem that's been built up over the past 10 years since Mont Blanc started.
And I take this question as a system integrator. We want to be ready with the complete family of product ARM-based, showing the best performance and energy to solution numbers.
So I think this will probably be our last question because we're about 2 minutes over, but it was posed to Jean-Marc. I said, you said the role of general purpose core is changing as accelerators are added. How do you think the ARM architecture should evolve to support this?
Well, this is a very interesting question because we address this question with the European Processor Initiative. In the first microprocessor architecture we are designing, we combine on the same die the ARM-Zeus core and RISC-V tile to test the technology, and a specific accelerator for the automotive domain from Calray, and a few other specialized devices for cryptography. This is why I would say it's already possible, because the ARM architecture and ARM IPs are very open, and because the ARM people are extremely helpful to make the integration of the interface at the NOC level very easy. So in the future, what's next? Maybe some open, let's say, interfaces, in order any accelerator designer could plug directly their accelerator on the ARM NOC or something like that. I don't have a definitive answer, but I would say that it's already possible to combine ARM with accelerators, and it could become much easier maybe in the future, depending on ARM willingness to release some open interface. That's it.
Excellent. So we're over and we're running into the next panel session. So I would like to truly thank everyone for attending and for all of their comments. Does anyone have any final comments before we bid everyone to fondue?
Thank you for hosting, Steve.
Yeah,
Thank you
thanks.
very much, Steve.
Cheers,
Thank you.
Steve.
Not a problem. Thanks, everyone.